everyone, and welcome to Shared Memory Performance Beyond TCP IP. I'm Andrea Exton-Camper with Hazelcast, and I'd like to present to you Ben Cotton. He's our panelist today, and he's been an IT consultant for the financial services for the last 20 years. His recent post is at JPMorgan, and he's very active in the Java community. You may know him from being a Java community process member or from his numerous JSRs that he is a member of. Today, Ben is going to give us a presentation, and afterwards we'll have the chance to ask some questions. You may ask questions by using the question box in the control panel, and Ben will attend to those at the end of the presentation. And without further ado, I'll turn it over to Ben now.
My name is Ben Cotton. I'm a Java programmer. I'm a Java programmer who has a specific interest in products like Hazelcast. Namely, I'm interested in JCache implementations that can deliver distributed grids. And most importantly, I'm interested in products like Hazelcast that can deliver ultra-high performance with regards to that capability. This presentation is going to introduce a product called OpenHFT. OpenHFT is the brainchild of Peter Lorre, who's somewhat of a legend in the high-performance Java community. OpenHFT stands for Open Higher Frequency Trading. I'm an IT consultant in the financial services area, and my clients, like JPMorgan, have insatiable appetites. And by insatiable, I mean literally insatiable. Their mandates for the highest throughputs and the lowest latencies are uncompromising. And they put their money where their mouth is with regard to that appetite. They pretty much have infinitely deep pockets, and they're willing to pay any price to get marginal capability that will accommodate their needs for the highest possible throughputs and the lowest latency. OpenHFT is a very ambitious and even disruptive kind of product in the sense that it really takes Java to a place that Java hasn't traditionally gone to. And we'll go into the exact details of that. What you'll notice in this presentation is that I'm going to have an extreme bias towards a use case that's not very popular. The bias I'm going to have is towards the HPC, the High Performance Computing Linux supercomputer use case. Now, that's a very rare kind of platform for the typical Java, user or consumer. We deploy our JCache data grids onto a supercomputer that has 240 CPUs and 3 terabytes of main memory. It also has InfiniBand as a physical interconnect provider. Now, this is not a computer you'll typically get at Best Buy, where you'll find Ethernet and a couple of gig of RAM at the most. But anyway, my bias is towards supercomputers because that's an area where Java is frankly quite delinquent in accommodating. If you go to the HPC Linux supercomputing community, Java is not a very dominant player, especially the JCache or the JGrid participants. And this presentation is going to show you how OpenHFT accommodates Java as a potential join point for the Linux supercomputing community. So let's just get started with the presentation. Okay, let's see. How do I do it? Okay, all right. Now, when we talk about high-performance computing, one thing we cannot tolerate is a Java virtual machine doing what's called this garbage collection activity. It's a stop-the-world garbage collection activity that is it's the original sin of Java and its unattractiveness to the supercomputing community. The notion that this virtual machine will cease all activity to garbage collect itself is absolutely a delinquency that we cannot tolerate. So it's relevant to what we call medium-lived objects. Okay, if you have short-lived objects in Java, they'll die in either Eden space or one of the survivor spaces. If you have long-term lived objects, they're going to get promoted to tenured space where they'll live happily and not be collected. But if you have medium-lived objects, they'll get promoted from the from Eden to the survivor spaces and often to the tenured spaces, where they will then die and have to be collected. So it's the medium-lived objects that caused this monstrous problem. And it's not an exaggeration. This is a nightmare for supercomputing applications. We cannot tolerate a virtual machine stopping we can't meet our service level agreements if the whole grid stops. Now, the fault of this is the fact that Java puts its objects on an in-process heap. Java has this traditional mandate of write once, run everywhere, and that accommodates all kinds of native operating system platforms. You know, Java runs on Linux, Java runs on Microsoft Windows, Java runs on an AS400, and Java runs on a Z90 mainframe. Okay, by taking that lowest common denominator approach, Java doesn't use the native operating system memory resources. It uses a heap that's on the process of the operating system. So, this is the cause of the garbage collection problem. Is this managed runtime requires the garbage collection to be done by the platform and not by the code. So, what's a remedy that can get us to, survive this this stop the world garbage collection? Well, what we do is we take our data structures off heap. And one of the great things you'll see about OpenHFT is they're a very compelling leader in terms of the off-heap ambitions of Java applications. They pretty much, in my clients' world, we build what are called quantitative risk grids, where we have these huge number of nodes, and we deploy onto these Java grid nodes what we call our computational operands, which act as basically hash maps. And of course, we have computational operators, which are highly complex quantitative risk algorithms that operate on these operands. Now, by going off heap, we survive the notion of having to endure these garbage collection events. Okay. Now, when we talk about OpenHFT, what type of hash map are we putting off heap? Is it the traditional hash map? Is it a synchronized map? Is it, one of the concurrent hash maps that give you both concurrency and thread safety? Or is it something different? Well, the answer is it's very different indeed. OpenHFT has a branded product called the Chronicle map. And the Chronicle map is OpenHFT's Java off-heap concurrent hash map solution. The exact API for Chronicle map, there's the package name for the API. Throughout the presentation, I'm going to give you links to all the OpenHFT resources. It's a very compelling product, and for those in the supercomputing community that wish to use Java, OpenHFT is pretty much a must-have. Now, what exactly is OpenHFT? Well, it's 100% open source, and by that I mean 100% open source. There's no little nooks and crannies that are closed sourced to accommodate some revenue for a part of the product. It's all open. If it's written, it's open. Okay, if it executes, you have the source for it, and it's designed to empower higher frequency trading. It's as simple as this: if you can access a price in the market and compute your algorithm to see if the spread on this price gives you the opportunity to profit, if you can do that faster than the other people, then you're going to make money, and the price will change while the others execute their orders. So the notion is this: the first to execute their orders, they get the profit. And those who come in second, well, they're going to have a higher price if they're on the buy side, and they're going to have a lower price if they're on the sell side. So they don't get the profits that the first come, first served kind of winners get. A great thing about OpenHFT is it gives these super strict service level agreements the ability to survive some of Java's known delinquencies. And you can actually achieve real-time compliance with this product. Some of the OpenHFT is divided into a number of subproducts and packages. They have a package called Java Lang that gives you garbage collection-free marshaling and serialization. You get thread safety, IPC safety. We'll talk about that. Chronicle Q is for logging and low latency queue data structures. Chronicle Map, which is the one that I use. That's the whole basis. Chronicle Map can be a basis for a JCache kind of implementation or an off-heap capability to a JCache provider. There's other products too. Chronicle Engine is something new coming in. They have a runtime compiler that when you build your value objects in your map, All you have to provide is an interface. We'll go over that. OpenHFT provides Java thread affinity. Now, when you're on a Linux platform with 240 CPUs, you may have a need to distribute some of the work onto some of the CPUs by affinity, meaning naming the CPUs, identifying the CPUs. OpenHFT has the ability for you to pin work onto specific CPUs. And they have transfix. Fix is a Wall Street protocol for requesting for quotes and order management and trade capture. OpenHFT provides a specific fix engine that's very low latency and high performance. Now, why are we interested in OpenHFT? So OpenHFT is an open source solution that empowers Java developers to deliver the highest performing and most flexible data locality. Now, by data locality, I mean you can choose to be on heap or off heap, and OpenHFT gives you a fabulous API and infrastructure for achieving that. The data locality takes advantage of native operating system resources. Now, that's very different from traditional Java. OpenHFT takes you from that write once, run anywhere, like lowest common denominator type of entrapment with Microsoft. OpenHFT allows you to take advantage of native Linux resources, and we'll see that specifically. So off-heap is a big feature, data locality. Now another thing, and by the way, that data locality off-heap is specifically in shared memory. Another thing it does is it allows you to use native IPC as a transport. Now by transport, we mean how do we communicate between grid nodes, okay? Typically, that's in the Java community, all I've ever seen is UDP and TCP as the available transports. Now that's fine if you're on a Best Buy computer and you're using like network interface cards to scale out. But scaling out does not necessarily mean going over a network interface card to a remote server. You can scale out in the supercomputing community by just adding blades with no network interface card hops. Now, when you have such an architecture where you're not going over network interface cards, you don't want to use UDP and TCP. Okay, that's going to cost you microsecond latency. With OpenHFT, you can have IPC transport that use native Linux resources, and you get nanosecond latency between grid nodes. Now, this is very, very impressive, and it's disruptive in terms of what it means to the potential for JCache and JGrid providers to accommodate the supercomputing community. Well, we'll show you with demos. It's breathtaking what it can imply for the supercomputing community. All right, so let's start part one, and let's move kind of quickly in terms of like we're going to walk through how we go off heap with OpenHFT. All right, the main ambition for going off heap is that we survive and never endure. Well, actually, we shouldn't say survive. By going off heap, we never ever endure a stop the world garbage collection event. Okay, so that's our motivation for going off heap. That's how we do it in OpenHFT. All right, again, the notion of a hash map has its history in Java. Let's do a quick history of hash map. Okay, the vanilla, most basic intro hash map is, well, it's a key value data store, but it's completely unaccommodating if you have any type of multi-threading. It's perfectly unsafe. If you operate with multiple threads on a vanilla hash map, you will suffer quickly and your data will become corrupt. Now, Java on process, on heap, gives you a static method from the collections API that you can take a reference from a vanilla hash map, and you'll get returned a reference to a thread safe hash map. Okay, just call this collections API invoke, and you'll have a thread safe hash map. But is that really any good? Well, it depends on your contention. Okay, this type of hash map is very, very highly contended. Only one lock on the entire data structure covers every key value pair. So literally only one thread at a time can operate safely. Even though it is operating safely, it's highly contended. If you have the notion of multiple threads accessing it, these threads are going to wait and your throughput's going to suffer. Now, with Java 5, Doug Lee delivered to the world the Java util concurrent hash map. Now, this is actually a pretty useful data structure in the sense that it uses lock striping to achieve multiple multiple thread safety and true concurrency, meaning you can have, depending on the number of locks you have in your stripping segments, you can have that many threads running concurrently. This greatly reduces contention. So that was a huge contribution to the Java collections capability with concurrent hash map. Now, what then would be wrong with current hash map? Well, concurrent hash map is still vulnerable to Java's mortal sin, the original sin, which is stop the world garbage collection. In the supercomputing community, we cannot allow that to happen. The stop the world garbage collection event betrays all our service level agreement. So CHM, concurrent hash map, is not good enough. What we need is concurrent hash map to go off heap and use native Linux resources that will never allow us to suffer a stop the world garbage collection event. And that's what OpenHFT does. With the combination of OpenJDK and the Chronicle hash map, by going off heap, we'll see exactly what happens. Here's a view of what happens on heap. I hope y'all are generally familiar with this. It's a pretty important understanding to have. As objects are created, they are born into Eden space. On certain minor GC events, they're going to be promoted into what's called a survivor space, a survivor segment. On a full GC, those objects that still are in the survivor spaces get promoted to the tenured generation. And it's there that they live until they become dereferenced or become garbage. Once they become garbage, being collected in the tenured space means you're vulnerable to a stop the world garbage collection event. This next slide here is really the most important slide probably in the whole presentation with regard to getting to learn the OpenHFT capability. Let me just walk real slowly through this. I hope you guys can see my mouse. What we have here is the architectural view of a Chronicle map, okay, which is a concurrent hash map, but it's not. Now, let me drop this. If you look here on the left, on the western section of the screen, you're looking at a process. This circle here represents a Linux process. Okay, if you do a PS minus FLEW, you'll see the process ID of this Java virtual machine. This Java virtual machine here has code executing on it that's going to take an interface provided by a user, go through the OpenHFT API, and create an off-heap bridge to an off-heap Chronicle map. Now, this Chronicle map here is not in the process address space of this Java virtual machine. I'm going to show you a use case where we have an actual, like a simple stock application, a fixed income bond, a high yield bond or something. We're going to show you how we provide an interface for a high yield bond and put its price ticks, intraday price ticks, off heap in a way so that this data structure will never survive. It will never have to endure stop the world garbage collection that would take place. It was off heap in the virtual machine. So once we have price ticks mutating off heap for this bond, I'm going to demonstrate also with the OpenHFT APIs and the code samples how the second process can read the price ticks that were written off heap. Now, this process also never has to endure a stop the world garbage collection event. So in the fury of market conditions where price tickets are mutating portfolios of bonds, we're going to show that by keeping this key value data off heap, we never endure a stop the world garbage collection. Because the horror would be if we mutate a price tick and this machine goes into a stop the world garbage collection and can't consume that price tick because all the threads are doing a stop the world garbage collection. That's the kind of thing that, bankers' pagers will go off and programmers will get fired because the bank's going to lose money if this thing's doing a stop the world garbage collection event while price ticks are mutated. This penguin here, there's a lot of penguins here. Java has a penguin icon, and Linux has a penguin icon. This is the native Linux icon. This penguin is a serious bird. It does not tolerate stop the world garbage collection events in its address space ever. So this penguin here, when it's heat, fine and good. It's a managed runtime. It's safe, and you don't have to worry about your own GC. But this pig one here doesn't allow that type of nonsense to take place in its address space. It uses memory map files to use temporary file systems, and it also uses /dev/shared memory, which is an operating system Linux view of shared memory. Okay, let's take a, okay, this is step one. Step one, you provide an interface, okay? For a bond, we have an issue date, a maturity date. We have a method that allows us to add atomically to the maturity date. We have as a symbol, okay, like a QSIP, okay, and we have a coupon, which is the rate of pay. Now, also within a bond, okay, we keep a array, okay, of the intraday prices at the given hour. So this array will have 7 index positions representing the start of the hour of the trading day. And the different prices that we keep, well, this is all financial stuff, but there are prices called call prices, par prices, bid and ask prices. All these prices will be kept in this nested interface. Now, as a programmer, this will represent the value object of your concurrent hash map. Okay, going back. Okay, hold on 1 second. Going back, this is step one here. Okay, so the programmer provides the interface, which I just showed you in this page. Okay, now by providing that interface, we pass this into OpenHFT, and that interface generates what's called an implementation of the Chronicle map. Okay, I'm going to show you all these details in code. But step one is provide the interface, and step two is going to be generate the Chronicle map that builds the off-heap bridge. So just provide the interface, an in-process compiler that's provided by OpenHFT will build the implementation class and give you the bridge to a true shared memory custody off-heap Chronicle map. So let's show those steps. Okay. Here's how you build a Chronicle map off-heap from the interface. You have what's called the off-heap updatable Chronicle map builder, and you pass into it the string, which this is a key value pair. So the key value is a string which represents a QSIP, okay? And the interface is, well, the interface is what you just created, the bond value interface, okay? So the in-process compiler will take this and, whoops, the in-process compiler will take this interface, okay? And on this call, it will build a Chronicle hash map right here, CHM. Okay, hold on, sorry. Now, once you have this reference, okay, to a Chronicle hash map, okay, you can build a writable context that goes off heap. It'll require a lock that will give you IPC safety, not just thread safety, but process safety, and isolate all mutations on that Chronicle hash map. Now I'm passing in a QSIP for this reference that was constructed in the data value classes invoked. And then I can just set values on the bond. I can set the issue date, September 15th. I can set the maturity date. I can set a 5% coupon, okay? And then I can start mutating price events on this off heap. So this code right here builds a bond with this QSIP, this maturity date, and sets these prices, and it's storing this all right here in the native Linux address space. Okay, let me check it. Okay. All right, so moving forward, I'm going to move a little bit quicker now. So this was step one and step two. So now you have right here prices mutated off heap. This activity is never ever vulnerable to stop the world garbage collection. Now let's look now at how in step. Well, here's another view. This Chronicle map is off heap. It's in the native address space of the Linux operating system. It has nothing to do with the Java virtual machine of any kind in terms of custody of the key value pair. Let's move now to see how the second process can read from those price mutations. Okay, so this is a second process. This is code executing. Again, they use the off-heap mutable, off-heap updatable Chronicle map builder. That Fluent builder allows you to get a reference to the Chronicle hash map. Now, which Chronicle hash map are you going to get a reference to? Well, you're going to get a reference to the one with this QSIP, 369.60413. So looking at it from this view, okay, Now we're pulling in, okay, a view to this data structure, which is that QSIP, okay, but we're doing it from a different process, and we're doing it with full IPC safety, not just concurrency management across threads in a VM, but concurrency management across processes using interprocess communication IPC. So now, once we get, once we read, okay, read context, okay, we get a read context into that QSIP off heat, and then we say, well, is it a 5% bond? Okay, and all these tests will pass. Okay, so we're using off heat ability to store the notion of a data structure that can't be vulnerable to stop the world garbage collection. Okay, the locking that's done is also kept completely off heat. When we go into the summary of what's going on here, it'll be quite impressive as to exactly what's taking place. Again, now, also from process 2, we can update the entry. So process 2 might not only just want to read mutations, it might want to mutate itself. So again, we take this, we get a write context now, okay, and we start mutating that context. And again, this goes off heat from process 2. Okay. Now, a couple of things you can do is you can also do your own locking. OpenHTFT supports the notion of atomic addition. Okay, it has atomic compare and swap. Okay, so also from process 2, if we want to add atomically the maturity date, now this is a little interesting. That's something you typically don't do. Let's say we want to add 30 years to the maturity date. That's a nice little computation there. So that takes the maturity date out to 2044. And if you want to make it a 0 coupon bond, well, you just add the negative of the current coupon. And this is all done with process IPC safety. Okay. Now another thing you can do is you can do explicit locking, just like you have read-write locks and the concurrent API re-entry locks. OpenHFT gives you multiple process locks, not locking against thread access, but locking against process access. We can mutate the symbol, changing the portfolio from IBM to OpenHFT. And of course, in the final, we unlock that entry so that other processes can compete for access. This slide here is a summary of what we just demoed right here, and it's pretty impressive. What we demonstrated that not only can you have multiple thread-safe operations on concurrent access to a hash map, a concurrent hash map, you can have multiple process safety, inter-process communication safe operations. So not just threads competing for your concurrent hash map, but Linux native processes concurrently competing for access to the data structure. You also have IPC atomic operations, okay, not just thread-safe atomic operations, like atomic integer gives you compare and swap and add this kind of stuff. Well, we have process. OpenHFT provides process safe. Another thing that's important is this is 0 copy. Okay, now I didn't do a pretty good job demonstrating this, but in typical Java caching and Java grid type of applications, any type of intranode transport or any type of computation across grid nodes involves a serialization and a deserialization. Okay, by necessity. Okay, that's another thing I consider kind of like a Java original sin, the notion that you can't have a call by reference capability on these data structures off process. Java is fundamentally call by value, and this call by value is by necessity, well, the definition of call by value is you endure a copy. OpenHFT gives you the ability to realize a 0 copy capability. Again, that's something very uncommon in Java, very disruptive to the notion of Java having a need to do a marshalling and demarshalling. Now, when you do have to do marshalling and demarshalling, okay, or if you prefer to, you're going to have the capability to do that without garbage collection burdens. And that's also important. Again, the whole purpose of this from this view, the whole purpose of this view is to never have to endure a stop the world garbage collection event. one of the big things that you should take away from this code demonstration is that OpenHFT has the ambition to provide the symmetry of Java util concurrent across Linux processes. Now that's big, okay? Java doesn't have any accommodation for cross-process, unless you're doing Java.net and stuff like that. The notion of having a concurrent package that accommodates cross-process isolation and synchronization, that's incredibly impressive. It gives you the ability to take advantage of native Linux resources that are very powerful and that are appropriate to use. I mean, my gosh, the C++ community has been using System 5 IPC for decades, certainly since the 80s. And it just doesn't make sense that Java would lock itself out of using some of these decades reliable native operating system IPC facilities. And another thing that you haven't seen yet, but you're going to see soon, is that by using native shared memory as a transport and not necessarily going over just a waste of time OSI loopback stack over TCP/IP, you'll achieve nanosecond latency instead of microsecond latency. So let's move on towards talking about that now. Just some statistics, important things. When you use the Java util concurrent hash map and you're grinding away at tests on hash map sizes that get into 250 million entries, 500 million entries, well, on this, by the way, this is Peter's machine. He's got a very nice 32 CPU, 128 gig memory. I think that's his desktop, actually. It's pretty impressive. I have a little bit of envy with this desktop. But his 128 gigabyte of memory, 32 CPU, his Linux, I think it's running Fedora 20. His Linux machine, when the concurrent hash map that comes from the Java package reaches 500 million entries, it's going to run out of memory. It can't even accommodate that. And this is a monster machine. When he has 1,000, when he has 1,000, well, when he has 1 billion, I guess that's a billion. When he has 1 billion entries, okay, and he's doing this type of throughput updates, okay. Oh, I'm sorry. Okay. So sorry, I missed this one. This is the one. Concurrent hash map, okay, with 250 million entries, okay. At some point, it's going to suffer a garbage collection stop the world time of 496 seconds, okay. So that's close to 10 minutes of garbage collection time where your grid is not doing anything, okay. This is unacceptable, okay. These GC times here cause Java not to be a player in the high performance HPC Linux supercomputing world. Right here is the reason. Imagine rendering and aggregating risk on algorithmic trading deployments, and your grid stops for 496 seconds. It's an absolute ridiculous delinquency, and it was what keeps Java from participating in these in a lot of these ultra high frequency algorithmic trading deployments. If we take the if we take a Chronicle hash map, okay, well, look at 1 billion, okay, even 1 billion entries, there's no GC of any time at all, okay, no GC at any time at all, and the throughputs, the throughputs are on par with, so without any GC suffering at all, you get basically the same throughput. So it's a super important win for the Java supercomputing ambition. Let's look at another thing that has the potential. Okay, now with all due respect to Hazelcast, a lot of my clients use the Infinispan JCache implementation, but the notion is this. And I know Hazelcast has some way of writing a data container that allows them to use their offshoot capability. So with the same regard in which Hazelcast uses some type of data container API, OpenHFT, okay, is being integrated with a potential Infinispan build as its offshoot provider. Now, this is all research stuff. The progress here hasn't been done much, but the ambition is what's relevant. in fact, the notion of having like, I don't know, there may even potentially, just musing openly, talking kind of aggressively here, the notion of there being like a many-to-many relationship between off-heap providers and JCache providers, I find attractive, okay? Frankly, the notion that Hazelcast has one, and it is closed source, I hate to, it's well known that it's closed source. Hazelcast closed source off-heap implementation, I think is the only one that it accommodates. To me, it would be attractive if the Java community embraced the notion of any JCache provider could accommodate any off-heap provider, and maybe Greg or Greg, of course, is the JCache. Greg Luck is the JCache spec lead. Maybe the notion of I don't know, maybe some later JCache release could embrace that as a standard potential. It would certainly serve the community. There's no doubt about that. The notion that, well, where Finispan has the ambition to generically plug in any data container provider through this interface. Well, if it's OpenHFT, you can take, we can create a class called OpenHFT's JCache implementation. Now it extends their vanilla Chronicle map, and it implements it implements JCache, and it implements the provider's data container bridge to the off-heap provider. So, to me that's a big capability that should be provided in the community. Just as a comment, the notion that the JCache providers currently accommodate only one off-heap provider, and that is in of themselves, that's not attractive to me. I'd like the notion of any off-heap provider to any JCache provider. There's an SPI that accommodates that marriage and that join point. So, in summary of the first part of this, and I know there's let's see, about 5 more minutes. I'll go past this second half, and it's pretty easy. The notion of what happened here is you have this notion of Java wanting to do a stop the world garbage collection. It's in its nature. But with the combination of OpenHFT, the OpenJDK, and native Linux, you can protect a Chronicle map, and it can go off-heap, and it will never ever have to worry about this garbage collector to impact it. This data structure is impervious to any type of stop the world garbage collection of any kind. All right, part two is very definitely biased towards the supercomputing community, but it gives Java caching and Java grid providers the opportunity to start thinking about doing things other than UDP and TCP. Because frankly, UDP and TCP, I mean, that's 1970s technology. And in the Linux supercomputing community, there's this thing called Rdma. And, in C++, you have native access to device driver APIs and Section 2 system calls that execute in the kernel, where you can do Rdma in C++, and you can get true zero-copy transport that don't involve the operating system at all. And UDP and TCP over a supercomputing deployment that has no network interface hops, that's just a waste of time, and it's disrespectful to supercomputing deployments that Java only accommodate UDP and TCP. That's just a comment. So let's go through this quickly. Okay, here's the old ancient, how many decades? This is the Osi model of networking layers, and at the bottom of at the bottom you have the physical layer. That's what at Best Buy you get an Ethernet card and an Ethernet cable. And if you shop from one of the, the giant supercomputing providers, you get an InfiniBand physical layer. Okay. Moving up the OSI stack, you got peer-to-peer, POET, peer-to-peer over Ethernet. You have the IP networking layer. Okay. In Java, you have an API that supports that. Java.net.inet address will give you IP datagrams. Here's the traditional Java, and I don't know of anything else besides TCP and UDP that's provided for in Java. Again, you have the Java.net API and the Java.io API that accommodate the transport layer. You can have server sockets listening on ports, and you can have socket writers that write the ports. You have session layers and presentation layers in the OSI model, but there's no Java APIs that accommodate this. Okay, and moving up to the application layer, you have the traditional, well, these are the very popular APIs that accommodate HTTP, FTP, and things like that. Now, this OSI model of the network layer is so old, and it's TCP and TCP is a guaranteed reliable network transport, and I don't know. It's time to give away guaranteed reliability of a network transport in favor of some aggressiveness. I mean, I don't know. You'll just see what I'm talking about soon here. With Java 7, there's a way to get rid of TCP/IP from your transport stack. Now, the problem is that it requires that you have InfiniBand as your physical provider. Okay, but with InfiniBand as your physical provider, and using Java 7, you can configure what's called Sockets Direct Protocol. And a Java application buffer can go from the network interface card across InfiniBand to the remote system's network interface card straight into the application buffer. Now, this is amazing because you talk about zero copy. Well, the only thing that's doing the copy here is the silicon on the network interface cards and the virtual machines that are configured with Socket Direct Protocol. So what you're getting here, well, note TCP/IP lives in a device driver on the operating system. So if you have this, you have true RDMA, remote direct memory access. Okay, now that's the direct bridge. You're going buffer to buffer, and these fancy like Haswell and Sandy Bridge CPUs that do amazing things, they're no longer burdened with transport of copying data across grid nodes. Okay, you can let Java 7 and SDP take that with a zero copy transport across only the physical interface cards. Let the cheap silicon on the network interface cards do the work, and don't burden these fancy, impressive, complex instruction set computers that come from Intel, the Haswell and the Sandy Bridge. These are impressive machines, and they should not be burdened with doing copies. They should be doing zero copies. So now, moving on, what does this mean in terms of having SDP? Let's take a quick look. I know we're running to an end here. Let's take a quick look at what happens with SDP. Okay, so here's a Java 7 virtual machine configured with SDP listening on a server socket. Let's say it's a JCache grid node. And let's say over here is a Java 7 virtual machine that writes, okay, one JCache grid node writing to another one. Well, with SDP, Socket Direct Protocol, it goes to the interface card and POW, writes directly to the Java buffer. This is one step, okay? One simple step over the native verbs device driver, okay? Now this will only work in Linux, okay? But that's important because you have a capability to do something. Now, if it's Java 6, look at this nonsense, okay? Here's another Java virtual machine, okay? A grid node. And here's another Java virtual machine grid node, but these two are Java 6. Now, if you're going to go over, if TCP and UDP are your only transports, and you don't provide RDMA over SDP, look what you have to do. You have to go to the Ethernet driver, then to the IP. Well, first you have to go to POET, peer-to-peer over Ethernet. Then you have to go to the IP layer, then the TCP or UDP, then you have a socket layer. Okay, you have 5 steps over the OSI layers, and it's completely unnecessary. By the way, this code is executing in kernel address space of the operating system, which means your fancy Haswell and Sandy Bridge processors are not doing zero copies. They're beasts of burden with regard to accommodating this code that gets one grid node to another grid node's application buffers. So where Java caching and grid providers are doing TCP and UDP, please consider making the step to where you can go to SDP over RDMA. Okay, you really will be respecting the supercomputer deployments. Well, if you do this and you try to sell to supercomputer people, you're not going to get any affection at all. Now here is an amazing thing that's happening. This just happened last year, I think. Intel has a product called iWork. Okay, now where current Java 7 requires InfiniBand as the physical provider, and no one has InfiniBand. You don't go to Best Buy and get InfiniBand. You go to Best Buy and you get Ethernet. Well, with Intel iWork, you can have, well, and this might happen in Java 9 or Java 10, but you can have Socket Direct Protocol over 10 gig Ethernet as a transport. And what this means is Java 9 or some future version With SDP over 10 gig Ethernet, you'll be able to deliver Rdma to everybody. Okay, so this is a huge thing. This Intel contribution is now in OPED. You know, the Open Optical Fabric Enterprise drivers. It's all open now. Intel contributed. So the notion of SDP over Ethernet is a true option right now. Just a couple more slides and I'll finish up here. Now, what does this mean with regard to OpenHFT? What it means is OpenHFT will accommodate native shared memory as a transport. So in addition to UDP and TCP, we can have transports over native shared memory. Now watch what happens with this. By the way, this is Peter Laurie. He's the founder of OpenHFT. He's something special. He's a real treasure in the low latency, high throughput communities. His attitude is exactly what's most impressive to me. He wants to be disruptive with regard to improving capabilities. And disruptive is exactly what he is. The ambition to use native shared memory as a transport is, wow, I can't tell you how you sound. Well, you know, the glory is it's the glory. It really. I'll show you why it's the glory right now. Last couple of slides. Okay, with dev shared memory transport, you have zero copy capability. Okay, because you're using a call by reference. Okay, now for those parts of your value objects that can't do zero copy, you have a copy by value tolerance. There's zero garbage collection. The value object capacity is limited only by your physical RAM. Our test at JPMorgan show that off-heap over dev shared memory is 438% faster than on-heap for key value pairs. Our average latency is 350 nanoseconds. Okay, now this has since dropped a whole lot. Now there are some drawbacks. Okay, the value objects are not fully transitive. Okay, Peter's made some progress on this, and the notion of the notion of any type of JCache standard that accommodates this is not even in the drawing boards or anything. This is all research and development kind of stuff, but the merits are compelling. So here, I'm running out of time. I'm going to go real fast here. Sorry about this. Here's some tests. I sent to Andrea a link to this whole PowerPoint stack. Here's the proof is in the pudding. Okay, what do we get when we use OpenHFT as the transport provider instead of the current Red Hat InfiniSpan? Now, when we have OpenHFT and dev shared memory is the key value custodian, native Linux, okay? This is what we call a ping pong latency test, okay? I have two terminals. One's a Java process that represents, if you picture a ping pong table, this process represents the player on the left side. And this process represents the player on the right side. And what we do is we just ping pong across shared memory a coupon mutation, okay? So now what happens when we do that with OpenHFT as the transport provider? Well, the coupon transports in 37 nanoseconds, okay? And it's very consistent, under 100 nanoseconds for sure. By the way, the full results of this test can be found here, okay? Now, here's the little X term showing. This is the left player, okay? The green, and the purple is the right player. So he pops over a coupon of 4, and then or a coupon of 5, and he pops back over a coupon. So across shared memory, they're following these coupon mutations, and they're doing it a round trip of 36 nanoseconds. That's because they're using shared memory and not TCP/IP as a transport. Now, what happens when you go to InfiniSpan or presumably Hazelcast or any JCache provider that uses TCP/IP as a transport? 92 microseconds instead of 40 nanoseconds. So this is, this is 1,000 times slower. Okay, without exaggeration, this is 1,000 times slower. Now, if you're on a supercomputer that has no network interface hops, and you make me go over TCP/IP, and I have to do a price of 92 microseconds, when I could, in fact, be using OpenHFT and realizing a cost of 37 nanoseconds, then your TCP/IP solution as a transport is offensive. Okay, that's no exaggeration. Now, have the ambition to be disruptive for the supercomputing community and get rid of TCP/IP. That's the message I have. Anyway, that's about it. Okay. These steps here just comment on JPMorgan things that we are making notes about with regard to our ambition for OpenHFT. We want to render and aggregate liquidity risk in real time. Okay, that's an incredibly difficult problem. And if we have IPC transports that are 1,000 times faster than Red Hat or Hazelcast or Coherence or anybody else that doesn't use dev shared memory, then we're going to use that solution, okay, because it's 1,000 times faster. That's it for the presentation. As a final note, I wanted to give Peter's explicit email. Peter Lorre is the brainchild behind this entire product. He works with his crew of brilliant programmers across the world, and they deliver the OpenHFT solution. You can find Peter's email address here, and everything regarding OpenHFT is at this site. That'll also refer you to the GitHub repositories that give you anything. That can give you everything you ever need with regard to this sort of stuff. So that's the presentation. I guess, Andrew, if you have people with any questions or anything, we can move that now. Okay, that's a very good question. Okay, who has responsibility for cleanup of the Chronicle map? They have an API. Okay, now this of course is something that you have to realize when you get these benefits. All right, you're returning to the notion of you have custody of when you allocate yourself off heap, you also have the custody to deallocate off heap. Now, OpenHFT has an API that accommodates you for that. It also has the ability to configure policies of how you want to manage the deallocation. All right, but the answer is this: the API has the responsibility. The runtime does not, because you're not involved with the runtime anymore. The question is this: is the full hash map locked to provide process safety? That's an excellent question. The full hash map is not locked. Okay, just like concurrent hash map accommodates multiple threads with locked striping segments, the Chronicle map accommodates multiple processes achieving concurrent access and mutation by providing segments that are off heap. So the answer is the full hash map is not locked. It's the Chronicle map, in terms of concurrency versus safety, acts exactly like Java's concurrent hash map, except the Chronicle map provides it for a process view, and concurrent hash map provides it for a thread view. Okay, so that's all for now. All right, great. Thanks, everybody. Been a pleasure.
Thanks so much, Ben. And as always, we'll be putting the recorded webinar as well as the slides on hazelcast.com. Thanks for attending, guys.